All right, here we go. This is problem number 36 from chapter 6 of the Holiday and Resnick textbook. It's on worksheet 6.2 for you guys in my class, at least at the time I recorded it, unless I moved it. So anyway, it says the terminal speed of a skydiver is 160 kilometers an hour. What? Terminal velocity, 160 kilometers per hour. I'm going to do some real quick factor label behind the scenes here. And that turns out to be 44.4, repeating, meters per second. Okay? Oh, and then they give you this other terminal velocity of 310 kilometers an hour. I'm going to, again, convert that. That turns out to be 86.1 meters per second. I need to find a way to distinguish between these. So this one is if you're spread eagle, and this one is if you're in a nosedive position, head first. Okay? So, assuming that the diver's drag coefficient doesn't change from one position to another. Seems like a weird assumption to me, but I guess that's possible. And then find the ratio of the effective cross-sectional area in the slower position to that of the faster position. So, all right, so here's the deal. One of the equations that we learned in class was this. Sorry, I lost my pen for a second. The terminal velocity is equal to 2 times the force of gravity divided by that coefficient times the density of the fluid times the area square rootified, right? Okay. So what I want to do is I want to rearrange this thing and solve for A. So if you do that, square both sides and do some algebra, you end up getting this, that the area of your object is equal to 2 times the force of gravity over c times rho times your terminal velocity squared. So just your terminal velocity there is being squared. Okay. So here's the deal. We're trying to find the ratio between the area in the slower position to the area in the faster position. So I want to find what's the ratio of the area in the slower position to the area in the faster position. Oh, well, that's just 2 times the force of gravity over c rho area. Nope, sorry. All I'm doing is substituting this in, okay? So this is going to be velocity terminal in the spread eagle position squared all over 2 times fg over c times rho times the terminal velocity in the nosedive position squared. So it's important to notice that these forces of gravity are equal, these coefficients are equal, and the density of the air hasn't changed. So everything here kind of cancels out. So if you cancel everything, the 2's cancel, these cancel, everything cancels except for your terminal velocities. So you end up getting 1 over VTS squared over 1 over VTN squared. Right? So let's see. So that's the same as VTN squared over VTS squared. Right? Just by you multiply both sides by VTN squared. Right? These guys cancel out. Okay, so anyway, so what do we get? You know what, it turns out I didn't even need to convert my units. So I did extra work for nothing. So anyway, you're going to get 310 squared over 160 squared, and that gives you your answer, 3.75. All right.